Hey everyone, welcome back and let's write some more neat code today. So today let's solve the problem, maximize the minimum powered city. And before we get started, I just want to quickly say that everybody's tough when the daily Leetcode problem is an easy or even a medium, but when it's a hard one, that's when people come crawling back to Papa Neetcode. If you're watching this video or even attempting to solve this problem, you should feel good about yourself because usually when there's a daily problem, like the number of people online trying to solve it is usually like at least like 2,500 or 3,000. And right now it's like half of that. And that's because when people see a hard problem, they immediately give up. Or when they look at the editorial and the editorial doesn't really explain what's going on or how the solution works, they give up. But you and me, we don't give up. And so let's get into it. I'm just going to go ahead and spoil this problem for you and say that we are going to implement binary search to solve this problem. But I wouldn't focus on that from the start because honestly, that optimization is the easy part. Don't focus too much on that because the editorial really glossed over the important part of this problem, which is not the binary search part. It's really the brute force solution. Like, how does the brute force solution even work for this problem? And then how do we optimize it? And then how does that naturally lead us to eventually the binary search solution? That's what we're going to try to focus on. So first, let's understand the problem. It's not really trivial. So in this example, we have this input array and we have an R parameter of 1 and we have a K parameter of 2. So the idea is that these are a bunch of stations. Each value represents the number of stations in each city. Now, there's a second array that is sort of derived from the first one, which is going to represent the power to each city. So for each of these, we're going to have a corresponding value. Let me show you how that's going to be calculated because it's going to be pretty important to this problem. So the idea is that this R value tells us that each station has a range of 1. They go in both directions. So they explain that to us with some absolute value math, but I'm going to ignore that. The idea is basically for this city rather, which has 2 stations, that means that not only do these 2 stations provide 2 units of power to this city itself, but it also provides it to the neighboring city on the right. So over here as well. So we put a 2 here, and we would also put a 2 over there, because it goes in both directions. Now, if this R was a 2, that would mean that this range would extend further. It would go 2 in this direction, 2 in that direction. Obviously, there's nothing over here, but that's fine. Like, we're not going to add power to nothing, but we can kind of just ignore that. Now, this city also is going to supply 1 unit of power to itself. So it's going to be 3 over here, and also to the neighbor on the right. And we're going to get 3 over there, and also to the left, but there's nothing over there, so we don't worry about it. And then over here, 4 is going to give 4 units of power over here. That's going to become a 7. Down here, going to become a 6. And then on the right, we'll put a 4. And then over here, this 5, same thing. I'm going to put 11 here. This is going to turn into a 9. This is going to turn into a 5. And then this 0, I mean, it could supply power to itself and its left neighbor. It doesn't have a right neighbor, but I mean, it just has a number of stations is equal to 0, so it's not really supplying any power. And that was assuming that the range was 1, by the way. That's kind of what the power array would look like. So you can see that in terms of computing like the power array, we could probably do it with like some kind of sliding window or something like that. I don't know if there's a sliding window approach that could really optimize it, but the brute force would be something like n, where n is the size of this, multiplied by 2 times the range, or to be more precise, it'd be something like 2 times the range plus 1, but it's still proportional to n. So, I mean, that's one way to compute like the power array. Now, I'm going to continue like running with this idea of having the power array, but let me just be upfront and tell you that this itself, I'm pretty sure is time limit exceeded. This will not get you a passing solution for this hard problem. We need a better way to do this. It's not crazy complicated. I will show it to you, but it's not really obvious if you're a beginner, especially. And when I say beginner, I mean like if you've only solved even like 100 or 200 problems, like I wouldn't expect you to immediately come up with something like this. And actually on second thought, I think I'll just show you how to optimize this right now rather than showing it to you later because we're already covering this right now. So I think it just makes sense. The idea is that we don't necessarily even need like the precise power array. We don't need to know the exact power of each city. We can sort of create an array that's almost going to give us the power of each city just by using the prefix sum of the array. So like if we wanted the power of this city, we would have this. And if we wanted the power of this city, we'd have this. And the reason we're going to do it this way is not only because then we don't have to compute the power array, but also because what this problem is asking us, I'll finally cover that, with this second k equals 2 parameter, what we want to do is among all of these powers, I'm just going to put some random values here, 1, 2, 3, 4, 5. We want to know what is the minimum of all of these. Right now, it's 1. So 1 would be the return value. What's the minimum power of any of these cities? But what we're trying to do is take whatever the minimum happens to be and try to maximize it. And we are given, in this case, 2 operations for us to do that. By operation, we mean that we can take the original array and add a station to any of the cities. So if I want to, I can add a station here, or here, or here, here, or here. Now, you tell me, in this example, like if we have all these powers, where would I probably want to add the station? I probably wouldn't want to add it over here because there's already a power of 5. I probably wouldn't want to add it here, already a power of 4, or here. I'd probably want to add the station either here or here, because if I add it here, well, it gives us a range of this, or if I add it here, it gives us a range of that. Now, probably we're going to want to add it here because it covers this guy and it covers an extra guy as well. So you're kind of seeing a little bit of the greedy nature of this problem. And so that brings me back to my original point. When we are adding a station, so assuming I already have the power array, if I add a station over here, well, if I want to update the power array, if I want to maintain it and I want it to be accurate, now I got to iterate over that range. I got to iterate over the range 2 times r. And I have to do that up to k times. It's not like that's a crazy inefficient thing to do, but we can do better. So instead of maintaining the actual power values, what we're going to use is this technique called a difference array. And the concept is actually really simple. Like I'd say that this concept itself is like a Leetcode easy once you understand it. Consider we have an array, and rather than tracking the actual power values, we track the delta. So in other words, like if I was to add a station over here, just one station, what I'm saying is I want everything in this range to be incremented by 1 in terms of like the power of each of those. But I don't want to have to scan through this entire thing because, I mean, right now the range is small, but if R was bigger, it could be a bigger range. I want to be able to do this operation in constant time. So the concept is really, really simple. You might be able to guess it right now. What I'm going to do is I'm going to say over here, put a +1. That tells us that starting from here, everything is going to have a range or a power of +1. But eventually that's going to stop. Like this is the wall, and everything after that has to now not have that power of +1. So we're going to not over here, but right outside of it, we're going to put the opposite. We're going to put a -1. And now the idea is that, like, assuming all of these are accurate, like we only populated one of them, a +1 here and a -1 here, but now, if all of these differences were accurate, like every time we increase the power, there's a plus value. Every time we decrease the power, there's a negative value. Well, then this prefix should tell us all of the powers that apply to this spot. This prefix should tell us all of the powers that apply to this spot. And it keeps going like that. And by the time like we get over here, now we want all the powers applying to this spot. And that's why we have the -1 over here, because that +1 stopped over here. It doesn't apply here anymore. So that's why we have to take it away. Now, obviously, there's probably going to be some plus values populated over here as well. That's what I'll show you as I go through like this example of populating this difference array. The concept is pretty simple. The implementation requires like some math, and you want to make sure you're not off by 1. And I'll cover that more in depth in the code. But for now, when we're here, when we're at 1, we're saying, okay, well, there's one station here. So we're going to put a +1 over here. And now we're going to put the -1 at this index, which is I plus R, which is going to put us over here. And then we want to be outside of that because this is the range and we want to put the minus value over here. So we're going to put a +1 there as well. So I plus R plus 1. So we'll end up with a -1 over here. Now, how did we get like the left value? Like how did we put the index over here? It's not actually just a straight I to I mapping. What we typically do is take this index, which is I, and actually subtract R from it. That'll be more clear when I populate this one. So here we want to go all the way left by just 1 and then to the right by 1 and then add the +1 to be over here. And I guess I'll color code it to make it even clearer. So we take I minus R, that's going to put the value over here. So the left value is always going to be positive. So +1, and I'll also add a +2. And then this value over here is going to be negative. So it stops applying there. Next, let's do this one. So 4 is going to be positive over here, and it's going to be negative over there. And this guy, it's going to be positive over here, +5, and then negative over there. And we're actually going to add an extra spot in this array. The reason for that is kind of the math. I feel like it'd be easier to explain in the code, but I'll try to briefly cover it now. It's mainly that when we calculate like that position, if we were out of bounds there, then we'd say, okay, well, then let's just place that value over here. But that value shouldn't actually apply to this spot. We shouldn't take 5 away from this spot because that's actually within the range. So we just have this extra spot here as like a dummy value so that if there is an extra, it'll go over there and it won't affect anything, because like this value is not really going to apply to anything over here. So that's kind of like our dummy spot, and we will actually need that. So it is pretty important. So I will put that -5 over here. And then lastly, we have this guy, 0. So we don't really do anything. We can put that +0 here, but it doesn't do anything. And then this typically would go even one value further out. And I mean, you could have that if you wanted to. It wouldn't cause any problems, but it's not necessary. We'll just put that over here in a -0. The way that position is going to be calculated is we're going to say I plus R plus 1, as I said before. But what if this goes out of range? Well, we want the max value to be whatever the index here is, which I think is going to be n, where n is the length of this. So this will be the minimum of these two values, just to make sure that we stay in bounds. Similarly, on the left, where we had I minus R, we're going to take the max of that and 0 to make sure that we don't go out of bounds in the other direction. Okay, so now you know how to populate this difference array, but you might be wondering, well, how is it actually useful? And that's going to be really clear as I just kind of go through this picture now, because this prefix now gives us this and this. You can see it like it's color coded, right? And now over here, this prefix gives us this, this, and this, which is these three. It's color coded. That's exactly what we would want. And this prefix over here gives us this, this, and this, which is these three. And it also gives us the 5, but then it takes away 1. So it took that guy away. So now you see why we did it, right? Because for 4, we want this range. It works perfectly. It works beautifully. So just by computing the prefix sum, we can get the power of a particular value. So if we scan from left to right, we can do that. But not only that, now, if we wanted to perform an update, like if I wanted to add a station over here, let me use a different color. If I want to add a station over here, then all I have to do is say +1 over here and -1 over here. That's it. We do it in constant time. Okay, so far so good. Now, how do we use this idea to even solve this freaking problem in a brute force way? It's not easy. So I mentioned the word greedy, I think, in this problem. And what that means is basically, of course, if we only have a limited number of choices and we're trying to increase the minimum power of any of like these values, the prefixes, I guess, of course we'd want to go for the smallest one first, right? So I guess one thing you could do is just somehow like scan through here, find whatever the smallest one is, and then apply the increment to that range, the one that includes the smallest number. And in this case, I think that would be this range. And yeah, you could do that, but even then, there's going to be possibly multiple choices, because what if it was this value we want to do? And let's say our window is of size 4. We suddenly have many choices. We could do this window, we could do this window, we could do this window, and I guess it's just those 3 in this case. But then how do we even know for those windows which one is the right one? Maybe we try all 3 of them. So all of a sudden, it's becoming a backtracking, really inefficient solution. So not trivial. Let's try a completely different way. Let's try to simplify our thinking, even if it ends up having a really bad brute force solution. What kind of simple thinking could we apply to this problem? Because that's usually how a greedy solution is going to work. It's usually pretty simple. You just have to make a couple assumptions. And my assumption is going to be this one. What is the solution set of this problem? Well, what's the smallest possible power that could be the solution to the problem? Well, it could be the minimum value. Like that's the possible smallest result that could be the case. Now, in this problem, 0 is not going to be the solution. But theoretically, it could have been if I just changed the example a little bit. What if I were to take a few of these and turn them into zeros? Now there's 3 zeros. And what if I change R to be 0 as well? Okay, so now we have 3 zeros, and we're allowed to do 2 operations, but each of those operations can only apply to a single station. So I guess I could increment this one, and I guess I could do this one, but then one of them is going to stay a 0. So that's why I'm saying that theoretically, the smallest possible value, let's call it low, is going to be whatever the minimum happens to be here. You could also use the difference array to get that as well. The difference array will give us like the power of each of these. And theoretically, that is also going to be the lowest value as well. And maybe that one would also be like slightly more efficient, but it's not too important. We're just trying to create like a valid solution set range. It doesn't need to be the most precise. So let's say for low, we'll take the minimum of the stations array for low. Like that's the theoretical smallest it could be. Well, the high, the largest theoretically it could be, is not like obvious how to calculate that at first, but theoretically knowing like these are all of our station values, what if the range of this was big enough so that like for each of these, it covered the entire size of the array? Well, then we would basically say that every single one of these values summed up together could apply to any of the other stations. So we'll take the sum of this, but there's more to it than just that, the sum of stations, because we still do have some operations left, k equals 2. So theoretically, those k equals 2 operations could apply to the entire array. So the highest possible value theoretically we could have is this plus k. Now, how can we use this range to solve the problem? Well, the brute force, a greedy way, would be to try the biggest possible one, the biggest possible result that it could be. Because once we make that assumption, once we say that, okay, we want to try this value. In this case, I think it'd be something like 3, 9, 14. So let's just make it concrete. And let's say our range is going to be 0 up until 14. So let's assume that 14, or that's what we're trying to do. We're trying to make every single one of these have a power of 14. Once we make that assumption, it's a lot easier to check if that's actually valid or not, because this is what we do. We be greedy. Once again, we're greedy. We start at the beginning and we say that, okay, this value, the power of it, which we can compute going left to right, just maintaining the prefix sum, this is 3. Well, that's definitely less than 14, and we can only do 2 operations, so theoretically, we could only increase this guy up to 5 if we wanted to. Well, all of a sudden, 14 is no longer possible. Let's try the next one. Let's try 13. And we'd keep doing that until we got down, I think, to 5. And then for 5, we'd say, okay, we have a 3 over here. Theoretically, we can increase it by 2. If we do that, basically what we're doing is we're saying, okay, add a plus 2 over here, and we're going to extend, since this is the left boundary, we want to actually extend the range to the right by a 2 times r, because we're not actually in the middle, we're actually at the left boundary, so we're going to do 2 times r, that's going to bring us here, and then we're going to do a plus 1, which is going to bring us over here, and this is where we're going to put the minus 2, because this plus 2 is no longer going to apply when we get there. So that's exactly what we're going to do. We put the +2 here. Right now, our current sum is 5, and we put the -2 here. Now I'm going to keep going. Now we're here. And by the way, when we add the +2, we're basically saying that the number of stations here is no longer 1, it's actually 3 now. So it does make sense because 3 stations plus 2 gives us 5. Okay, now we're here. So we add a +4, and that makes sense because this 4 is applying here as well. So we had 5, we add a +4, we have 9. That's good. 9 is bigger than or equal to 5. And then we'd kind of just keep running through it. Now we get -1 plus 5, and then I think that would give us like 13 or something like that, which is bigger than 5. So far, so good. Then we get over here, which is going to give us a -4. I think that's going to bring us down to 9, still bigger than 5. Then we go over here, -4. We are now down to 5. It does make sense because this 5 applies here. The 0 doesn't do anything. So we're at 5, still greater than or equal to that. And then we're pretty much done. We don't really need to go any further than that because there's no more stations left. So what we did is we validated this 5. We found out that yes, 5 is a value that we can achieve, and it's the biggest one. We know that because we worked our way down from the top to the bottom. So that's how we do it. And if you're wondering why this works, again, it's basically like the greedy assumptions that we made. Because when we get to this value and we see that this one is not big enough, we know exactly what to do. We don't care about anything that came before because we already validated everything that came before. We're going to apply the k increment however much we need. In this case, we needed 2, but maybe we only need 1. Then we would have just done the 1, and then that would have depleted this down to 1. But in this case, it actually depleted it down to 0. But that's what we would do. And we wouldn't just apply it here. We would apply it to everything that comes ahead. We don't know that everything that comes ahead actually needs the operation, but we know for sure that nothing behind us needs the operation. That's why the choice becomes simple. So that's like the assumption. That's why greedy problems are really, really tricky. You need to make certain assumptions, and once you do, the problem becomes easier. So those are mainly the points that I wanted to cover. If you got this far, I really hope that you can understand now how to apply binary search to this. It's literally just taking the brute force, going from top to bottom, rather than doing that, just doing binary search on this. So if you understood that, the time complexity then is going to become big O of n, because every time we run that validate function, we're going to have to iterate over the length of the array. And how many times we're going to have to do that is going to be log of the size of this range, which is going to depend on how big high is. And high is proportional to the sum of the array. Well, the sum is going to be, let's say, length plus r. So whatever this is. So log of that variable, n plus r, or we could call this x or some other variable if you want to. But that's the time complexity. I believe the values in the array are limited to some integer that isn't too big. So this isn't going to be crazy. But even if it was really big, log is a pretty efficient function. So even if this was a really big number, it wouldn't really matter that much. Okay, finally, let's get into the code now. By the way, if you're new to this stuff or this style of binary search problem is new, I would recommend checking out Leetcode.io and solving a few of these medium problems. I think Coco eating bananas, capacity to ship packages are some really good ones because they're not like the natural binary search that you run on an array. It's more of like running binary search on a range of values. But anyways, let's get into the code. First things first, I'm going to get the length of the input array. And I'll go kind of quickly for some of this easy stuff. So the difference array I talked about is going to be initially all zeros, and it's going to be the size of n plus 1. We need that extra value at the end so we don't mess up any existing values. And then we're just going to go from left to right. And what we want is to do this. We want to say that in the difference array, at index I minus r on the left side, we want to add the current value in stations array like this. And on the right side, we want to say I plus r plus 1 is going to have the station's value subtracted. That's when this stops applying. But we know that these aren't always going to be in bounds. An easy way to fix that is just have a couple of variables, which, I mean, I guess we could have just put those in line, but I think it's more readable this way. But I minus r, but that could be too small. We don't ever want it to be smaller than 0. And the opposite on the right side, we never want it to be too big. We don't want I plus r plus 1 to be bigger than n. And I'm intentionally putting n here, not n minus 1, because like I said, we do need that extra value on the right. If you don't believe me, try doing this on an example without it. You'll see what goes wrong. So now that we have those, we'll put left here and we'll put right here. And now I'm going to do my binary search setup. I'm going to, for now, put a can achieve function, I guess. And we're going to pass in the target P, the target power. And I'm not going to implement this yet. I'm going to show you how we use it first. So first, let's do this setup for our binary search, low and high. We're going to do this min stations and sum of stations plus K. And I'll quickly just show you like how the brute force solution would work. Like we do something like this. We do for I, or for target P in range from low to high plus 1. This is non-inclusive, so it'll stop at high. And we'd go in reverse order. And what we would do is just this, like if can achieve is true with target P, then we would just return that number, that target power. That's the largest one that we can achieve. And we know that this would execute eventually because low is definitely going to be validated. Low is the smallest value in all of those. So the brute force is just as easy as that. Now, optimizing it with binary search isn't much more difficult. It's just going to be a little bit of this. So first, we'll make sure that the pointers don't cross each other. Low is less than or equal to high. And to get the target P, we're actually going to compute the midway point of low and high. And if we can achieve it, we don't necessarily know that it's the biggest one. So rather than returning it, we're going to have a variable result, which I'm initially going to set to low because we know that it is a possible answer. It just might not be the biggest one. So then here I would set low equal to target P, I would set result equal to target P. And I would set low now equal to target P plus 1. Because if we can achieve this one, now we should try for something even bigger. If we can't achieve it, we should try for something even smaller, which is going to be target P minus 1. So our high pointer will be shifted in that case. After this is said and done, we can return the biggest one that we were able to find. Okay, now probably the most difficult part, I would guess, for most people is going to be finishing this function. It's not going to be super hard. You just got to make sure you do your math and your plus ones and stuff like that correctly. First, we're going to keep track of our current power because we know that we're going to iterate over this difference array, but the difference array, we're going to need like the prefix sum to know the power at each city. So initially we'll say current power is 0. We're also going to need to keep track of the K because we're going to possibly deplete some of those. So initially we'll say current K is equal to K. And lastly, this difference array, we're going to iterate over it, but we're also going to update it. So we're going to create a copy of it. So I'm going to say diff copy is going to be diff.copy. Okay, now we can start iterating from left to right. And we want to maintain our current P. That's like the first thing that we should do. So we're going to take the value in diff copy, not stations, and we're going to add it to current P. And now we only want to update like the current P if we actually need to. So target P is this and current P is this. So if current P is less than target P, well, we have to do something. We have to now add to this. But what if we don't have enough K to add to this? Well, then we have to return false. Like we know for sure we can't achieve it. So let's just add that check first. Let's say if target P minus current P is bigger than K, return false. And if it's not, well, then we can start updating our variables. We can say that we're going to take this delta, and actually we don't need K here, we need current K, very important. You can see how making like one mistake could completely mess up your solution, so be careful. So if that's the case, well, then we should subtract from current K now this delta, so just like that. And since we're using this in multiple places, I think it's fine to add a variable. I'm going to call it additional because that's the additional stations that we need to add to the current position. So let's change that to this, subtract that from that. And we have a couple choices. Well, I guess I wouldn't even call them choices. Like this additional, we definitely want to update current P with it. So we can do this, add to it like that. And I guess we could also do this, like diff copy at the current index, could add additional to it. But that's actually not necessary, because now that we took that additional and added it to the current power anyway, it's not necessary to actually update this diff copy position, because this is never going to be used again after like this iteration of the loop. But what's more important is to update the right value, which the index of that is going to be this. Right is equal to I plus 2 times R plus 1. And like I said, that 2 times R is because we're assuming that our current I is the left boundary, so the right boundary must be 2 times the length from that. And then the plus 1 is to go outside of that. So this right boundary could end up also going out of bounds. So kind of like how we did up there, we also want this to be the minimum of itself and n. And then we'll use this here. And rather than adding additional, that's the position where we're going to remove these additional. And there you go. So just a lot of bookkeeping, a lot of math to keep track of. But now that we do that, like the next iteration of the loop, we'll check the next spot and it'll kind of do the same exact math. And maybe we'll return false at some point. But if we don't, that means that every single position was validated. And down here, we can return true. So this is the entire code, about 35 lines. I'll go ahead and run it now. And of course, I had to have a bug, and it was a really sloppy one. So over here, I don't know why I did the assignment. This should definitely be an increment. So I really apologize for that. Like I said, it's really easy to make a mistake, but let's give it another try. And now you can see it works and it is very efficient. If you found this helpful, check out Leetcode.io for a lot more, and I'll see you soon.